Hi, everyone. My name is Jay, joined by Yunin, James, Yudan, and Iman. Today, our group will present the final design for Jindaka Intermodal Facility and related transport infrastructure upgrades. The project is located at the West Jindaka Airport along the boundary to Forest Field Rail Line. The facility will support containers movement between Fremantle Port, the Eastern State, and other feed destination. Because of the project, the surrounding road network will need to carry more heavy vehicles, especially on Nixon Road, Renfrew Road, and New Clifton Road axis. At the same time, Kennywell is already a busy residential, commercial, and industrial area. This road already have traffic issue during peak period. Therefore, the aim of the project is to provide an integrated design solution to improve traffic efficiency, feed access, safety, and multimodal connections.
Thanks, Jay. A key pillar of that transportation upgrade is the Nicholson Road and Clifton Road intersection. So, considering the projected future demand associated with the establishment of the facility, the Clifton Road Nicholson Road intersection is key as it provides access to the new terminal and is assessed to see if it could accommodate this growth. And as shown in the figure here, the existing intersection as it is to the present day operates under give-way control, where vehicles exiting Clifton Road must find acceptable gaps in the both northbound and southbound traffic of Nicholson Road, which has a peak hour volume of 2,000 vehicles per hour, so extremely significant. And under assuming a 10% increase in Nicholson Road traffic and a 30% increase in Clifton Road, Sidra predicted that the intersection would operate under complete breakdown, with a level of surface of F, a significant degree of saturation, and a substantial delay of 262 seconds per vehicle. And since Clifton Road does serve as that key freight access route to the terminal, it's clear that a substantial upgrade is required. And to improve operational performance, two key intersection upgrades were developed and assessed. The first one being upgrading it to signalized with the existing road geometry and incorporating a slip lane to improve turning capacity on the heavily trafficked Nicholson Road movements. Second being a roundabout with a key design feature of a southbound bypass lane, which allows the dominant Nicholson Road traffic to continue without actually entering the circular carriageway. And assessing both of these design options in Sidra under the same stream traffic conditions, both actually achieved a LOS A, so level of service of A, which is considered optimal. However, the differences in operational efficiency, safety, and freight performance influenced our final recommendation. And following our multi-criteria assessment, assessing all these, the adopted and recommended design is the roundabout with that southbound bypass. And as you can see, it's a 95% reduction in delays, degree of saturation, and queues, and also significantly improved safety to all the other designs and the existing configuration due to the slower access operating speeds upon access. And although this design does come at a greater cost, it is preferred as the bypass gives a greater traffic flow on Nicholson Road and making it viable in the longer term for the community and intermodal operation.
Thanks, Timon. Now I'll be talking about the design upgrades concerning the Nicholson-Ranford Road intersection. So the existing intersection is presented here and is a signalized control one. Sidra analysis was undertaken with the future traffic projections, and the results are summarized in the table presented now. As you can see, no approach operated at an LOS above E with a majority scoring F. Therefore, the current design and phases of the signalized intersection is incapable of sustaining the projected traffic volumes. 3 design upgrades have been proposed and are presented now. Multi-criteria analysis was undertaken, and the optimal design was determined to be design number 3. Design number 3 is a grade separated solution and replaces the existing signalized intersection with a 2-lane roundabout, incorporating lane extensions while preserving the existing full lane configurations of the intersection. An overpass is also to be installed along Ranford Road. In this design, a majority of traffic users can now bypass the intersection completely, resulting in a 49% or higher reduction in delays, saturation, and queues. The introduction of circulatory flow at the ground level improves the efficiency as the overpass now now reduces traffic volume, approaching the roundabout to a manageable level. Lost time now has been minimized as drivers can now make gap acceptance decisions and split lanes have been installed to further enhance efficiency. Finally, the roundabout reduces conflict points and operating speeds, which leads to improved safety outcomes. Zebra crossings have been installed along the right turn roads and a signalized stage crossing was selected for pedestrians on Nicholson Road. An indented bus bay layout was designed for buses operating in the eastbound direction, making it more convenient and safer for passengers to board and align, while in the westbound direction, a curbside bus stop was used given its spatial efficiency and was deliberately installed right in front of the signalized pedestrian crossing, allowing all buses to utilize the red signal timing for boarding and disembarking, reducing lost time.
Thanks, James. I'll move on to the Clifton Road interchange station part, where I will explain the layout and the design approach. The site sits next to the existing rail corridor with 3 access points of Ranford Road. 2 key constraints shaped everything, the rail line to the north and the waste transfer station to the southwest. These boundaries define our usable footprint from the outset, and the layout was built around them. The layout is organized around a clear access hierarchy. Pedestrians come first, followed by buses, pick-up and drop-off, and finally private vehicles. The station entry anchors the northeastern corner, and each mode has its own dedicated zone, radiating outward from that point. Buses enter through a signal-controlled intersection and run a dedicated one-way loop through the sawtooth base before exiting, completely separated from general traffic at all times. Private vehicles use a separate internal road along the southern side with distinct entry and exit points, so there's no cross-traffic conflict between modes. Pedestrians have right-of-way across the entire site, whether you are coming from the car park, the bus base, or the PODO zone. All paths lead to the station platform entry through the walkway network. The pedestrian bridge over the bus loop provides great separated access, so passengers never have to cross an active bus lane.
Thanks, Yudan. Right now we move to vision modeling. For vision modeling, each transport model was represented separately. Bus, vehicle, pedestrian, and rail passengers were assigned their own routes, design speed, and stopping behavior. This allowed the model to check how pedestrians transfer between different models and whether the internal circulation can operate without major confliction. For bus operation, the model includes 6 lay-by bus bays with 3 bays in each direction. And for the pickup and drop-off area, private vehicles were modeled with lower speed to reflect the station environment. 4 stopping bays were used to short passenger pickup and drop-off activities. For the parking area, 3 parking lines were provided to present park and ride demand. An additional pedestrian area was also created next to the parking area to simulate passengers park their vehicles and then walk towards Ranford Station. And for the Ranford Station was model used multi-layers. The base layer, platform layers, and the concourse layer were connected by the ramps. So passengers' movement between the platform, bus area, and pickup area could be simulated. The vision model provides a visual and operational check that the final interchange layout can support control transfer conveniently.
Thanks, Jay. So now I'll go through our container terminal design. So the container terminal is designed to handle 200,000 FEU containers per year, and the layout was driven primarily by the constraints of our chosen equipment, which is the Kalmar Reach Stacker. So one of the most significant considerations is that its lifting capacity drops substantially beyond the front row for heavy mining containers, which are 34 tons. So rather than the standard 4-row wide configuration that we see in the general containers, our mining bays are limited to 2 rows wide. So this keeps every container within the machine's rated capacity throughout the whole operation. That constraint led us to 3 bay types across the whole terminal. So we have 12 mining FEU bays, which we see in red, 7 general FEU bays in green, and 3 general TEU bays in blue, giving us 22 bays in total. So the terminal itself comes out to a 612 by 130 meter rectangle with the 22 bays running perpendicular to the rail line and spaced 18 meters apart to allow enough room for the equipment to maneuver. Containers are also stacked 5 high across all the bay types. The B double trucks enter from Clifton Road on the southeast side, and then they load and unload on the south side, then move clockwise around the perimeter and then exit. So the rail side is kept clear at all times. So for the terminal pavement, we considered 2 options. The first is a flexible foam bitumen pavement, and the second is a continuously reinforced concrete pavement, or CRCP. We're recommending CRCP, and I'll explain why. The reach stacker front axle load is 739 kilonewtons, which is applied repeatedly in the same location every day. So concrete handles that kind of loading better because it spreads the stress across the slab rather than concentrating it into the subgrade below. So the subgrade here is a mix of high plasticity and medium plasticity clay with a CBR of just 2%, which is very poor. The flexible pavement option needs over a meter of engineered fill just to compensate for that, while the CRCP gets there with 150 millimeters of lean mixed concrete subbase. And it also prevents clay fines from pumping up under repeated heavy loading, which is a real long-term risk on sites like this. So the terminal is divided into 3 pavement zones, each designed for its specific loading conditions. Zone 1 covers the perimeter road where the B double trucks circulate, and Zone 2 are the areas between the container stacks where the reach stacker travels and positions itself. So both zones have interior slab thicknesses of 250 millimeters, while the edge zones step up to 325 millimeters to handle the higher stresses at the slab boundary. Zone 3 is the post-load area, directly underneath where the reach stacker sets containers down. And this is where the loads are the most severe. So the slab thickens considerably to 800 millimeters. What really sets CRCP apart for this application is the elimination of contraction joints throughout all 3 zones. So those joints are typically where concrete pavements start to deteriorate. And for a terminal running continuously over 40 years, avoiding that maintenance burden is valuable. The upfront cost of CRCP is higher, but when you factor in life cycle performance and reduced downtime, CRCP is the stronger long-term investment.
So now I'll be talking about the terminal drainage design. A drainage system was designed for the terminal primarily for the stormwater management and flood risk mitigation and will drain to an evaporation pond. The drainage system was designed to accommodate a 20% AEP stop. To ensure no containers were stacked on a crown, a uniform grade of 0.4% east to west and a 1% grade of north to south was adopted. Maximum gully discharge was taken to be 60 liters a second. The rationale method was selected to determine the peak runoff discharge. The IFD curve variables were taken from the coordinates shown on the screen from the BOM website. A hydraulic grade line approach was then taken when designing the system, and the Colebrook-White equation and Missouri charts was used to determine loss coefficients. The final design of the system is presented now. A gully chamber system was adopted over a single gully connection system to improve the overall reliability of the entire drainage system. Now we look into detailed sections of the system, which is shown on the screen. The optimal spacing for the gully to handle the expected discharge was found to be about 17 meters apart from one another, while the distance between each gully and interceptor was designed to be 8 meters. Concrete pipes were chosen to connect gullies and interceptors due to their long service life and widespread availability.
Thanks, James. I'll talk about the evaporation pond design. The pond is sized using a monthly water balance rather than a single design storm. It is important because post-wet winters cause storage to build up progressively across consecutive months. Using conservative wet year rainfall data, the storage peaks in September at around 120,000 cubic meters, giving a design depth of 1.22 meters. At full supply level, under normal annual conditions, evaporation exceeds inflow, so the pond is self-sustaining with no routine external discharge. The pond is 600 by 180 meters with 3-to-1 side slopes. A 1.5 millimeter HDPE geomembrane liner was selected for its extremely low permeability and hydrocarbon resistance. The HAL at design flow sits over a meter above full supply level, so there's no risk of the pond backing up into the pipe system.
Awesome. Thanks, Yutan. Now we move on to the Clifton Road upgrade section. I will be talking about the geometric design. So Clifton Road is that red road shown on there, and it connects Nicholson Road to the terminal. For the design criteria, key parameters have been summarized in the table presented. The posted speed limit of the road was taken to be 80 kilometers an hour, and both the horizontal and vertical curves have been designed in accordance with Osroad Part 3 standard, as shown on screen. A plan view of the redesigned road is also displayed, and concerning the horizontal design, we can see that the proposed road can be separated into 3 main sections delineated by IP 2 and 3. 2 horizontal transitional curves are designed at these points, and the final design is now displayed with all key points labeled. This is the final vertical curve design with all key points labeled and consists of 2 sags and a crest. All longitudinal and crossfall grades were also deliberately chosen to be above 0.5% to ensure sufficient drainage conditions. The design surface was also designed on average to be about 0.6 meters above the existing surface to avoid cutting too deep into the surface where CBR decreases drastically. Note that the elevation rises drastically to connect to the reduced level of the terminal base height.
Thanks, James. So now I'll talk about the Clifton Road drainage design. So the stormwater drainage system for Clifton Road was designed to handle runoff across the full 3,857 meter carriageway based on the 10% annual exceedance probability event, so a 1 in 10 year storm. The road naturally falls towards a low point or a sag at around the 2,128 meter mark. So the geometry actually splits the road into 2 separate drainage catchments. I'll let Yudan go into a little bit more detail on this.
Thanks, Eunice. Starting with catchment A, it runs from SLK0 down to the sag point. Gully spacing was determined using the curb flow formula. We adopted a uniform 150 meters spacing throughout. That gives us 14 connecting pits in total. Pipe diameter step up progressively from DN 225 at the upstream end all the way up to DN 600 at the outlet as cumulative flow builds along the network. Catchment B mirrors that approach on the other side, running from SLK 3897 back toward the sag point. The same 150-meter gully spacing applies, giving 11 connecting pits. Pipe sizes step up from DN 225 to a maximum of DN 450 at the outlet. For both catchments, the HAL was verified using the Misri-Charts method. The hydraulic grid line stays below road surface level at every connecting pit throughout. At the sag point, both catchments discharge to a natural stream crossing, requiring a box culvert. The total catchment is 4.5 hectares. We adopted a 900 by 600 millimeter precast concrete box culvert, giving a full flow capacity over the requirement.
And in line with the upgrades to the drainage and in the vertical curve, to accommodate the heavy freight demand associated with the terminal, the pavement is also upgraded. In accordance with the project brief, a 40-year design life together with annual growth rate of assumed 3% is adopted. And the loading assessment includes both the general freight containers and the mining container movements, and which is primarily governed by the heavily loaded 34-ton mining containers which enter via rail to the container terminal and exit via Clifton Road. And with the considering the assumed vehicle as shown in the slide there, using Osroad's methodology, a cumulative loading over the design life is determined to be on the order of 10 to the power of 7, so extremely significant, and this forms the basis of the pavement thickness design. And using the 3 test pits and 6 DCP test data given in the geotechnical assessment, material classification and subgrade strength were undertaken. Using the Japan method from the surface to 1 meter depth due to our vertical profile minimizing cut, a 90th percentile design CBR of 5% was undertaken, which is quite conservative for our to accommodate for the long design life. And the investigation also identified predominantly clay soils with various levels of expansive behavior. And as shown in the table below, test pit A exhibited high plasticity and expansive potential. And as shown in the image here, noticeable differences in the soil color, texture, and moisture content are seen, with test pit A showing highly dark and cohesive clay profile, which is also identified as the most problematic. Test pit B and test pit C show more of a granular sandy material with lower clay content. And although some long-term deformation is going to be associated with the expansive subgrade behavior, the design incorporates conservative assumptions. And using the adopted CBR and the design loading, the pavement thickness was undertaken using Austroads. The final adopted pavement consists of 40 mil asphalt wearing course underlaid by a 2-coat primer seal to reduce moisture to the pavement structure, and considering the presence of highly expansive soil. But it is noticed that the asphalt surfacing layer serves as a wearing course and may need to be replaced sooner than the 40-year design life. And beneath this, 210 mil of crushed rock base and 380 mil of granular sub base is used, which accounts also for construction tolerances.
Thanks, Iman. The last part I will discuss is Nixon Road pavement rehabilitation. Nixon Road between Ranford Road and Clifton Road was identified as structural issues. This section will carry more heavy vehicles after intermodal facilities operating, so pavement strengthening is required. The adopted treatment is ensued from the B2 stabilization with 40 millimeters asphalt wearing course. According to pavement data, the DCP results show that the subgrade strength was not uniform. Therefore, Nixon Road was divided into 2 subgrade strength zones. Traffic load for Nixon Road direction include outbound general fatigue, outbound empty movement, and outbound mining containers movement. The south direction include inbound general fatigue, outbound empty movement, and outbound mining containers movement. After combining this with existing Nixon Road traffic, the northbound direction produced the higher design traffic. After circuit modeling, for the weakened section, its adopted structure is 40 millimeters asphalt over 330 millimeter FBS, while for the strong sections, 300 millimeters FBS is needed. Overall, the design provides a particularly rehabilitation solution for Nixon Road and support the future heavy vehicle demand over 40 years design period. So that's all of our presentation. Thank you for listening.